So now we're going to see what is the actual difference between a particle and a wave. So just to remind us, the last lecture we went over the Bohr model, where we had the atom almost looking like a solar system with these discrete orbits, n equal 1, 2, 3. And we said electrons, when they jump from a higher orbit down to a lower orbit, they emit photons. And we said the Balmer series, which were the visible in the visible range, were all jumps to the n equal 2 level. So when you jump from the 3 to the 2, that gave us that red line. The 4 to the 2 gave us the blue. The 5 to the 2 gave us that purple. Those are the 3 lines we saw. Now, if we look at the sun right here, remember the sun is a black body spectrum. We saw the black body spectrum. We get that signal that looks like this right here. We get all the frequencies. But if you look very closely, it looks like if someone took a vacuum cleaner and cleaned out certain lines on these. That is, you get all the colors except you're missing the colors, little strips here. They call this an absorption spectrum. And how do you get those? Well, if we look at this line right here, normally you get an emission spectrum from this. You get that red line. But let's just say the sun is putting off that frequency. It puts off all the frequencies. But you have an atom out here, hydrogen atom, and when this photon from this energy hits the hydrogen atom, it's going to kick the electron from the n equal 2 level to the n equal 3 level, and then drop back down. But when it drops back down, it's not going to throw it in the same direction. So that light that was coming out and hitting it, excited it, dropped it back down. It could be off in any other direction. The odds that it's going in the same direction is pretty slim. And so you get a decrease in that one frequency. So it looks like you get these absorption lines for all the elements in the sun. You can see 92 of the elements in the sun right here. From these lines, you get the temperature of the sun. And you can do it for other nearby stars. It tells you so much information on these absorption lines, not only the temperature, the composition, the speed, because you can use the Doppler effect. You can actually determine the magnetic field, because the stronger the magnetic field here is, it affects the lines right here. So you get so much information. That's what most astronomers are looking at, these lines. If you're looking at a nebula, where it's just a gaseous nebula excited, then you get emission lines. Or certain galaxies, active galaxies, you just get emission lines right here. But for the sun, you get the black body incorporated with the absorption. The absorption tells you what's in the atmosphere. Okay, just wanted to point that out. And so now we ended up the last time saying that, light, Einstein said light acted like a particle. We called it a photon, and we said the momentum is h over the wavelength. But the last thing I said was that de Broglie, in probably about 1920, early 1920s, said that electrons and protons were a wave. So we had both of these. It looks almost backwards right here, and he used the same equation. The wavelength of an electron is h over p. And that way, when you go back to the hydrogen atom, if you're saying that this is a wave, it has to line up. This thing can't be like 2.5 wavelengths. It's got to be either 1 wavelength or 2 wavelengths or 3, so that it all matches up. By saying that, that is the reason why the angular momentum was quantized, because the wavelength is related to the momentum, and the momentum is related to the angular momentum. Right here. So the wavelength is related to the angular momentum here. Okay, so now I really just wanted to say, what is the difference? If we're going to say light, which we thought was a wave, is now acts like a particle, and electrons, which we thought were a particle and now acting like a wave, what is the difference between particles and waves? Okay, so let's say we get something that we know is a particle, bullets. bullets shooting out of a gun. We know they're particles. So we have a little gun right here, shooting bullets. It sprays them out right here. And over here, I'm going to have a wall. Which has two openings in it, right here. Okay, I'm going to put my gun right in the middle, right there. So we're going to have a little gun that's right here that can spray bullets. And it moves, sprays it right here. Now, when the bullet hits over here, it cannot penetrate through the wall. It's just going to bounce off. Also, the bullet, the holes aren't that big. They're just a little bit bigger than the bullet. So I should probably make that a little bit closer down right here. Okay, some of these bullets are going to make it through the holes right here. Okay, and now back here, I'm going to have a back wall. And I want to know where these bullets are going to hit the back wall. So what I could have is I could have a little bucket here, fill it with sand, and we'll shoot a bullet. If we hear a clank, that means we knew it went through one of the holes and went into the bucket. So what I'm going to do is I'm going to slowly move the bucket this way. We'll put it here for a while, then move it to here, then move it to here. And I want to know where are most of the clanks at. That is, where would be the worst spot to stand back here? Well, if we did this experiment, first of all, just to make it simple, let's label these holes. I'm going to label this hole number 1 and number 2 on that one. Suppose we covered up this hole so that bullets could only get out through that hole. Then I would have expected most of the bullets' clanks would be right there when you put the bucket up here. And so if I were to plot out where you'd most likely see it, it would be right there. And it would probably go off like this. Now, you could still get hit over here because these bullets are just a little bit smaller than the hole, so they could bounce off and come over here. It could bounce off that edge and come up there. So this is the probability of just getting through the first hole right there. Now, if we cover up that hole and then continue this experiment, we would expect most of them to go right there. And I would expect some picture that looks similar to this, but peek down here, right there. Right there. So that would be the probability of just going through the second hole. Now I don't get a half a bullet, I always get whole bullets, so there's no half a bullet. Okay, and so now I open up both the holes right here. Now what do I get? Well, since the bullet can only go through one hole at a time, it can't go through both holes right here, I'm just going to get the sum of these two. So if you open up both of them, P12 would just be P1 plus P2. So it would just be the sum of these two. If I were to just plot out the two, let me see. This plus that, it's pretty much the same thing. It looks like, but right here it's this plus this, so it's probably something like this. This would be P12. So it looks like, that's not a very good place to stand. Why? Because you can bounce off this edge or this edge quite often, and you might get hit a lot. Okay, so this is the way that particles act right here. You add the probability of going through this way plus the probability of going through that way is the total probability of going through both. Okay. So we can also say the bullet either goes through hole 1 or it goes through hole 2. Okay, so this is particles. Let me just write over here. Particles. Particles. Okay, so now let's look at waves. Okay, so something we know is a wave, water waves. We know. So let's just say this is the surface of the water here, and we got a plunger over here that goes up and down. We got a plunger. Okay, and we have our same wall over here. Looks like that, and comes here. Now we send out our waves. So there's the crests of the waves as they're going. So I got some plunger going up and down. Plunger going up and down. Now, when this wave hits the openings right here, they start their own little waves coming off like this. Same with right here. Okay, and then we could have a back wall back here. And I can't have a bucket of sand out here. What we're looking at is we're looking at how much the wave goes up and down. So what I could do is I could have a little piece of wood and measure how much it goes up and down, how much the height changes going up and down. Now, one thing I don't want is I don't want reflections on this. So maybe I don't even need a wall. Take away the wall, because the wall will just give me reflections. And we'll just slowly move this up this way, and we'll see how much the wave that the wood bounces up and down right there. Well, again, if I were to block this one right here, I'm going to get a picture very similar to my P1 over there, but I don't measure probability, I measure intensity. Intensity is what you measure here. And what's the intensity? Intensity of the wave. Intensity. Well, that's proportional to the square of the height. That's actually the mean square height, but it's related to the height. Let's just say it's related to the height squared, the mean height squared. The reason why I have to square it is because the height goes positive, negative, and you average that out and you're just going to get 0, so you square it. So this is the intensity is related to how much this goes up and down squared. Okay, well, if I close off this one, I'm going to get something very similar to this pattern I had over here before, except this is going to be I1, intensity with just hole 1 open. This was 1, this was 2. And if I do for the second one, where I1 is equal to the H1 squared, where H1 is due to the height due to coming through hole 1. Now, if I close up 1 and we look at 2, I'm going to get, again, a pattern similar to this one down here, except it's not going to be a probability, it's going to be an intensity. This is going to be my I2, where I2 is, it's actually kind of proportional, but that's good enough for us. It's equal to H2 squared. The height due to 2 squared. Okay, so this is what I get from the 2 right here. Now, what happens if I open them both up? I do not get this blue pattern anymore right here. What I get is, I get a pattern that looks like this. We actually have that pattern when we did the laser in one of the first couple of labs we did. We showed the picture of the laser beam on the wall. You were seeing a pattern like this. I just put a hair in front of the laser. So you can go back and look at that one. But you get this pattern right here. Well, it's not I1 plus I2 like this. This was P12 is P1 plus P2, but I12 is not I1 plus I2. What you have to do is, for waves, I12 is equal to, you have to add up H1 plus H2 and then square it. So you don't square this and add them, you add them and square them. So that's the difference. Well, what does this give you? Well, if you were to square this thing out right here, I12, it's actually the first term squared plus the second term squared. But then you would also get a cross term in there. You get 2 times the first times the second, but if there's a phase difference between them, which there would be, because if this crest is hitting you, this crest isn't probably going to be there at exactly the same time. You get H1, H2, you get the cosine of some delta, where delta is the phase between these two waves. And so this I12 is just I1, because we said that was I1, plus I2. But now we get plus 2 square root of I1 square root of I2 cosine delta. Well, this is the interference term. Interference term. Right here. That is, the wave actually goes through both holes simultaneously, right here. And you'll notice, if we just looked at this spot right here, when we closed up hole number 1, that means you're only looking at I2, you got a lot of, the waves were really bouncing up and down here. You notice, just by opening this up, the wave here stopped. It seems kind of strange that it affected this one right here. With this closed, it was bouncing a lot. When I opened it up, it went away right here. It went pretty much to 0. Because these two are interfering with each other. That doesn't happen with particles. If someone throws a rock at your head, you don't say, hurry, throw another rock at my head so that the 2 rocks cancel each other out and I don't feel anything. You might try that with someone else, just don't have them try it with you right here. But the 2 rocks hitting you isn't ever going to cancel out to no rock hitting you. Here, 2 waves hitting you, they can both cancel each other out to eliminate the 2 right here. So this is the difference between a wave and a particle. The wave goes through both holes. Particle only went through this one or this one. Okay. So now we can go to an electron. An electron. Well, we'll come back to the same experiment with our walls. Okay, and then we'll have a gun that shoots electrons. So we're back to our gun, electron gun. Sprays electrons. Okay, here's our back wall. We can have our back wall here again. And our bucket, we can put the sand back in it. And when an electron goes into the bucket, it makes a little clang. Okay, so again, we'll move this thing up. We never get a half of an electron. We always get a whole electron in the bucket right here. So if we hear a clink right here, can we say that the electron either went through this hole or that hole? So can we say each detected electron, each detected electron, that is, it hits the bucket, each detected electron either goes through hole number 1 or hole number 2. Can we say that if you detect it right here? Well, again, we'll cover up, this is 1, this is 2. If we cover up 2, we get a peak right there. So again, we get this thing going down like that. That would have been the probability of 1. Then we close this one up. We get the same picture for this one, probability of 2. Now the big difference is when we opened them both up. Do we get the red pattern here or do we get the blue pattern? That tells us what it is. Well, if we open them both up, we actually get the red pattern. So we get this pattern right there. Wait a minute. The only reason why we got the red pattern before is because we said the wave goes through both holes and interferes with itself. Does that mean part of the electron goes through this hole, part of the electron goes through that hole, and they interfere with themselves? Not only that, if part of them goes through here, and I only measure whole bullets here. So can we say each detector either goes through hole 1 or 2? No, because if it did, I would get the blue pattern. So I cannot say this right here. I cannot say each detected electron either goes through hole 1 or 2. It must go through both. So this is not true right here. These electrons have to go through both. The only thing is, I only detect whole ones. That would mean that this math has got to work out. That is, this probability, P1, has got to be equal to some wave squared. Something that's waving. So I don't know what to call it, just psi right there, squared. So there's got to be some sort of it's a wave right here, and so that'll just be my wave. And likewise, P2 would have to be just like before, and P12 is going to have to be just like this with an interference term right here. So P12 is going to have to be P1 plus P2 plus the square root, 2 times the square root, 2 square root P1, P2, cosine of the phase angle between the two waves. So this is kind of strange here that the electron seems to go through both holes, but it's never detected in pieces. It's always detected as whole pieces. It's always a whole one right here. Well, wait. How about if we try to look and see if they really do go through both holes? How can we test that out? Well, what we could do is we could get a really bright light and put it right there, really bright. And if an electron goes through here, the light will bounce off of it, and we'll have a little scope here, and we'll look, and we'll be able to see, it went through here. Or if it went through here, we would be able to see a little flash on this side because the photon would bounce off of that one. Okay, so now all of a sudden we turn on the light, and all of a sudden we notice the electron does not go through both holes. It only goes through this one, or it goes through that one. It does not go through. So it does only go through one hole or the other. But the minute I turned on this light, this red pattern right here turned into the blue pattern. soon as I turned that light on, all of a sudden I got the blue pattern here instead. Turn it back off, get the red. Turn it on, I get the blue. Turn it off, I get the red. Well, let's try this. Let's turn down the intensity. Let's make it a little less bright right here. So if I turn down the brightness here, then I don't see every electron here because the photon doesn't hit every single electron. I only see some of them right here. Well, all the ones that I saw, if I separate that data out from the ones I don't see, for all the ones I don't see, I get the red pattern. For all the ones I do see, I get the blue pattern right here. So he's going to know whether I looked at him or not because he's going to act differently. Well, you might say, yeah, but remember, we said E was equal to HF. So instead of turning down the brightness, why don't we turn down the frequency? If we turn down the frequency, then we're not disturbing it so much because the energy of the light depends on the frequency. So if we come over here and we slowly turn down the frequency, then when it was up high frequency, we were seeing this. When it was at low frequency, we were seeing this. And when we slowly turn it down, it'll slowly meld into this. When does it go into this one? When you turn your wavelength, remember when you turn the frequency down, you're making the wavelength bigger. When your wavelength gets to be this big, then you're back to the red pattern. Because when your wavelength gets this big, you can't see anything smaller than your wavelength, so you can't tell which hole it went through. Once you can't tell which hole it goes through, you get the red pattern. So there's some sort of, it's like an uncertainty principle. It's called the Heisenberg uncertainty principle. It's impossible to know which hole the electron went through and get the red pattern. That's impossible. The minute you try to look and see which one it goes through, you get the blue pattern. So it's an uncertainty principle. You can't get both. You can't say, I know which hole it went through and get the red pattern. That's impossible. What would happen if we had 3 holes? If you had 3 holes, then the electron would split up and go into 3 pieces right here. You notice when we detect it, for some reason, it all comes back together again. Right here. It went through all 3, but if you detect it right there, it came back together. What about 4 holes? It'd go through all 4 holes. 5. What if it had thousands of holes? It would go through all thousands of holes, all at the same time. What if we had so many holes that there's no wall left? So I just have the gun here, and I detected it there later. How did it get from here to there? It went through every hole. Where's my holes? They're everywhere. So it went this way, it went that way, it went this way, it went that way, it went this way. You have to assume it goes every possible way it could go to get there. You have to assume those are all possibilities and then add them all up right here. So you'd have a lot more terms in here because this was just 2 holes. But if you had infinite number of holes, you'd have a lot of terms there. But you'd have to add them all up to get the true way that this thing went from here to here. It actually goes all possible ways right here, which is quite strange right here. And we're just talking about an electron going from point A to point B, or a proton right here. So it looks like electrons, when you don't look at them, they act like waves. When you detect them, they act like a particle. This electron acted like a wave when it went through here. It interfered, but when you detected it, it acted like a particle. If we come back to, if we look at, what about light? What if this were light coming through here? What if this were a light gun right here? Well, if you don't look at it, you get this pattern. If you start detecting the light to try to figure out which one, if you go down to 1 photon at a time, throw them one at a time, and detect which one they go through, you'll get the blue pattern right there. You don't know which one they go through, you get the red pattern. When we did the one, when I put the hair in front of the laser, I didn't know which one it went, so I got the red pattern right there. But if I would have thrown one photon at a time, I would have gotten the blue pattern. So it looks like electrons and photons are exactly the same thing. They both do exactly the same thing. They're both travel like a wave, detected as a particle, except photons go at the speed of light and have no mass. But in terms of waves and particles, they act exactly the same. Well, wait, why wasn't this bullet right here? Why didn't it act like a wave right here? Well, even if I don't look at it right there. Well, if I could do this and not look at it right here, I actually did get the red pattern. It's just that it would have looked like this. It would have looked like this. They would have been so close together that you would have never noticed it. All we saw was the blue right here, but they would have been so close right there. But so this is the strange thing about quantum mechanics, that everything is both a particle and a wave. They all travel as waves. They all detected as particles. Okay, and so there is just some differences. So now we're about ready to begin quantum mechanics. Remember, what we've gone through so far is we've gone through black body spectra, where Planck said that oscillating charges emit or are quantized, their energies are quantized. Then we said Einstein, with the photoelectric effect, said, no, the oscillating energies aren't quantized. What you're emitting from the oscillating atoms is quantized. It's the photon that's quantized. It's E equals HF. Okay, and then we looked at higher energies. We saw the Compton events, and then even still higher, we saw pair production. And then when we went to the atom, we said we had the plum pudding model until Rutherford, doing his scattering experiment, showed it was a compact nucleus. And so Bohr came out with his Bohr model. And again, we had quantized orbits, which, again, there's a semi-quantum right there. And then de Broglie said that electrons were actual waves, where this is the wavelength right here. And so you might say, what's the wavelength of us? Well, it depends how fast you run right here. But remember, h is pretty small right here. That's why we look kind of solid right there. We can't measure our wavelength. And we might say, well, what is it when you stop something? Well, you can never stop anything. Try to stop an electron. That's impossible. Right? How are you going to know it was stopped? You got to look at it. Once you look at it, you sped it up. So you never know whether it's stopped. Okay, so now that we had electrons being waves, now we can start in on quantum mechanics. We're going to learn a little bit of math first, right here, just to review a little bit. Okay.